Section 7.8, Graphing Square Roots and Other Radical Functions. Let's begin by taking a look at our family of functions of f of x equals x squared. We know it's a U-shaped graph, and on previous sections we determined that we could put this in vertex form and locate the vertex and know if I have a horizontal shift left or right, a vertical shift up or down, or if I would have a shrink or a stretch. When I do that, we'd know our domain is x between positive infinity and negative infinity, and we'd have y is greater than or equal to 0. We know that this passes the vertical line test, therefore is it a function. If I find the inverse of this, I end up with plus or minus the square root of x. Notice this does not pass the vertical line test, and it's not a function. But the domain is x greater than or equal to 0, and my y is between positive and negative infinity. Similarly, we also had g of x as x cubed. That's another one of our family of functions. We know that we could have a shift left and right, or vertical up and down, and we also know we could have a shrink or a stretch. In this case, we know that our domain is between positive and negative infinity, and so is our range. This also passes the vertical line test, and it is a function. The inverse of this would be the cube root of x. If we take a look at the domain, its x is between positive and negative infinity, and the range is also positive and negative infinity. It is a function, and it passes the vertical line test. What I have is the parent function, which is y equals the square root of x. We have a reflection in the x-axis, which would be a negative in front of the square root of x. We have a stretch if a is greater than 0, and we have a shrink if a is between 0 and 1. Reflection in the x-axis on that situation is if I make that a negative. I can have a horizontal translation if inside the radical I have something added or subtracted to my x. If it is a minus h, that is a shift to the right. That is our general form. If it is a plus h, that is a shift to the left. A vertical translation is determined by k. That value is on the outside of my radical. If it is a plus sign, that is a vertical shift up. If it's a minus sign, that's a vertical shift down. We can combine those forms into this form, which in this case I would have a shift of h, left or right, depending on this plus or minus, and a shift vertical up or down, depending on plus or minus of my k. That holds true for any nth root function. This page shows examples of horizontal shifts and vertical shifts of our parent function of y equals the square root of x. Here I have that parent function. If I substitute in 0 for x, I get 0. 1 for x, the square root of 1 is 1. The square root of 4 is 2, and the square root of 9 is 3. The other translations are based off of this function. Here I have y equals the square root of x minus 1. This is a horizontal shift to the right. So every ordered pair that is on this parent function is shifted 1 unit to the right. Here I have y equals the square root of x plus 1. That 1 is on the outside. That is a vertical shift of 1 unit. That's a representation of my parent function, but every ordered pair is shifted up 1 unit. On this function, I have y equals the square root of x plus 1. Notice this 1 is on the interior of my square root. Therefore, this is a horizontal shift. This is a horizontal shift to the left. That is my parent function, but every ordered pair is shifted 1 unit to the left. Here I have y equals the square root of, and then it says minus 1. The minus 1 is on the exterior of my radical. That is a vertical shift down. That's a representation of my parent function, but every ordered pair is shifted down 1 unit. Also, I have examples of the domain and ranges for each of those functions. Here's our procedure to graph a function using the parent function. I want to graph the parent function of the given problem. For example, y equals the square root of x. I want to use at least 5 points if possible. Depends how large it gets. Number 3, determine the translation of those points in the problem. Horizontal, vertical, shrink, or stretch. I want to move each point by the determined translation and plot. Graph each function and find the domain and range. I know that this function is generated by the parent function y equals the square root of x. So what I want to do is to graph that function first. I know that that is at 0, 0, 1, 1, 4, 2, and 9, 3. And I can graph that function. That is y equals the square root of x. I want to graph y equals the square root of x minus 7. To do that, I'm going to use these ordered pairs and just translate it the number of units specified. This is a minus 7 on the outside of my radical. Therefore, each one of those ordered pairs is going to go down 7 units. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And 1, 2, 3, 4, 5, 6, 7. And I connect those ordered pairs, and that is y equals the square root of x minus 7. On this function, I want to graph y equals the square root of x plus 5. I'm going to start by graphing the parent function y equals the square root of x. I know that that is 0, 0, 1, 1, 4, 2, and 9, 3. I can graph in those data points. And now all I need to do to graph this function is to have a horizontal shift of 5 units left. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then plot those points. And that is my new function. On this function, I have y equals the negative square root of x plus 4. This negative represents a reflection over the x-axis. So what I'm going to do is graph the parent function, y equals the square root of x, but I want it as a reflection over the x-axis, which would be y equals the negative square root of x. I still have 0, 0. If I plug in 1, I get the square root of 1, but that makes it negative. So 4, 1, 2, 3, 4 would be a negative 2, and 9 would be a negative 3. And then I can plot those ordered pairs. And now, to generate the function I need, all I need to do is do a horizontal shift left of 4 units. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And 1, 2, 3, 4. And that is the function that I was asked to graph. In this example, I want to graph y equals a negative 2 square roots of x minus 3 plus 4. To begin, I still want to graph y equals the square root of x. We know that to be 0, 0, 1, 1, 4, 2, and 9, 3. And then I'll just plot those points. Now what I want to do is translate that y equals square root of x according to this function. In other words, what I want to do is move each ordered pair to the right 3 units, multiply that y value from that ordered pair by a negative 2, and then add 4. We know that this is negative, so this is going to be reflection over the x-axis, so it's going to come down this way, somewhere vertically on the y-axis. So let's start by moving each ordered pair to the right. So we're going to move each ordered pair to the right. So this ordered pair goes to the right 1, 2, 3. The outcome of that is 0 for the y. 0 times a negative 2 is 0. 0 plus 4 is 1, 2, 3, 4. The next ordered pair is at 1. I move that 3 units to the right. 1, 2, 3. Its outcome is 1, 1 times a negative 2 is a negative 2. A negative 2 plus 4 is 1, 2, 3, 4. The next one is at 4. I move that to the right, 1, 2, 3. The outcome at 4 is, for y, is 2. 2 times a negative 2 is a negative 4. Add 4, I get 1, 2, 3, 4. If I move this out 3 units, I'm beyond the graph. So I can just plot my ordered pairs with what I have available. And when I do, my graph is going to look like this. Now I can verify that by just plugging in my x values. For example, 1, 2, 3. 3 minus 3 is 0. Square root of 0 is 0. Times the negative 2 is 0. 0 plus 4 gives me 4. 1, 2, 3, 4. 4 minus 1 is 1. Square root of 1 is 1. Times the negative 2 is a negative 2. Plus 4 is 2. And finally, 7. 7 minus 3 is 4. Square root of 4 is 2. 2 times the negative 2 is a negative 4. Plus 4 is 0. Now we have to determine the domain and range of this function. The domain for x is greater than or equal to 3. And the range, my y values, y is less than or equal to a positive 4. In this function, I want to graph y equals 1/2 square root of x plus 3 minus 5. I already have my y equals the square root of x graphed. So what I want to do is translate this function 3 units to the left, multiply the y output by 1/2, and then subtract 5. So to begin with, I have my x at 0. I'm going to move it 3 units to the left. 1, 2, 3. My output on 0 is 0. 0 times 1/2 is 0. And then down 5 units. 1, 2, 3, 4, 5. My next ordered pair is 1. I move it 3 units to the left. 1, 2, 3. The output at that 1 is a y value of 1. Times that by 1/2. 1/2 times 1 is 1/2. And then I move that down 5 units. 1, 2, 3, 4, 5. My next x value is 4. I move that 3 units to the left. 1, 2, 3. The output at 4 is 2. 2 times 1/2 is 1. And down 5 units. 1, 2, 3, 4, 5. And my last one is way out at 9. I'm going to move that back 3 units. 1, 2, 3. The output at 9 is 3. 3 times 1/2 is 3.5, which is 1.5. And then down 5 units. 1, 2, 3, 4, 5. And I can plot those ordered pairs. Now I can determine the domain and range. My domain, my x values, 1 to negative 3. X is greater than or equal to a negative 3. And my range, my y values, 1, 2, 3, 4, 5. Y is greater than or equal to a negative 5. Now I want to continue with the cube root of x minus 5. I have plotted the y equals the square root of x on previous slides. This is going to be a very similar process, except I'm going to use the family of functions y equals the cube root of x. I have the ordered pairs plotted already. The cube root of 0 is 0. The cube root of 1 is 1. The cube root of 8 is 2. The cube root of a negative 1 is a negative 1. The cube root of a negative 8 is a negative 2. Therefore, I can plot these points. And now just translate the ordered pairs specified in my function. And this is the cube root of x minus 5. So each ordered pair has to go down 5 units. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Then I can graph those ordered pairs. And that is my function, y equals the cube root of x minus 5. We can find the domain, x, such that x is all real numbers, and the range, y can be all real numbers. Again, I have my ordered pairs for the cube root of x plotted, so I can graph those in. That's y equals the cube root of x. Now I need to translate this 2 units to the right, since this constant is in the inside of my radical. That means that each ordered pair needs to move 2 units to the right. 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. Then plot those ordered pairs. And that's my new function, y equals the cube root of x minus 2. Domain, again, all real numbers. And range, all real numbers. Let's continue. We're going to have multiple translations here. Again, I have my family of functions, y equals the cube root of x plotted. I'll graph those in. And now each ordered pair needs to move 3 units to the left and 4 units up. So 1, 2, 3, I'll estimate, up 1, 2, 3, 4. 1, 2, 3, up 4, 1, 2, 3, 4. 1, 2, 3, up 4, 1, 2, 3, 4. 3 to the left, 1, 2, 3, up 4, 1, 2, 3, 4. And finally, 3 units to the left, 1, 2, 3, and up 4. 1, 2, 3, 4. Then connect my data points. And that is my new function, cube root of x plus 3 plus 4. Domain, x is all real numbers. And the range, y equals all real numbers. In this function, I have y equals a negative cube root of x plus 2. I already have plotted y equals the cube root of x. I know with the negative, I'm going to reflect each ordered pair over the x-axis, and then have a vertical shift up of 2. To do this procedure, I'm going to take each output on each ordered pair, multiply it by a negative, and then add 2. Here I'm at negative 8 and negative 2. Negative 2 times a negative 1 is a positive 2. Now I need to add 2. 1, 2. My next ordered pair, I am adding negative 1. A negative 1 times a negative 1 is a positive 1, plus 2. Here I'm at 0. 0 times a negative is a 0. 0 plus 2. My next ordered pair, I'm at 1. 1 times a negative 1 is a negative 1, plus 2. And finally, I am at 2. 2 times a negative 1 is a negative 2, plus 2. Now I can graph in my ordered pairs. And you can see that my function is reflected and shifted by 2 units up. My domain, x, again, is all real numbers. And my range, y, is all real numbers. Our next example, again, I have y equals the cube root of x already plotted. I want to reflect again over my x-axis because it's negative, but I have a stretch of 2, and I have a vertical shift down of 3. but I'm also shifting this to the left 1. So each ordered pair must shift to the left 1, take its outcome, multiply by a -2, and subtract 3. Let's begin with our farthest ordered pair to the left. I am at a x value of a -8. I need to move that to the left 1. The output in a -8 is a -2. A -2 times a -2 is at 4. 1, 2, 3, 4. At 4, then I subtract 3. 1, 2, 3. Let's do that again. Here I'm at the x value of a -1. I move to the left 1 unit. My output at a -1 is a -1. A -1 times a -2 is 2. And then I move it down 3 units. My output at 0 is 0, but I need to move it to the left 1. The output is 0. 0 times a -2 is 0, but I move it down 3 units. 1, 2, 3. My output at 1 is 1, but I need to move that 1 unit to the left. The output at 1 multiplied by a -2 is a -2, and then down 3 units. And finally, 8, I move to the left 1 unit. At 8, the output is 2. 2 times a -2 is a -4. And then down 3 units. Now I can plot my points. As you can see, my function is reflected over the x-axis. It has a shift to the left of 1 unit and a downward shift of 3 units. But my domain is still all real numbers, and my range is still all real numbers. In these examples, I want to rewrite each function to make it easy to graph using transformations of its parent function. Describe the graph. Here, what I want to do is simplify inside my radical. Y equals the square root of 16 is 4, square roots of x plus 2. In this situation, I have y equals the square root of x. That is my family of functions. I have a stretch of 4 and a vertical shift of 2 units up. Here, I have, when I simplify, the cube root of 125 is 5. Cube roots of x minus 3. My family of functions is y equals the cube root of x. A stretch of 5, but a shift down of 3 units. In this one, I have y equals the cube root of 25x plus 100 minus 3. I can factor a 25 out of my inside expression. That gives me x plus 4. Now I can simplify the 25 out. Square root of 25 is 5. Square roots of x plus 4 minus 3. So I have y equals the square root of x is my family of functions. I have a stretch of 5. And I'm going to go to the left 4 units and down 3 units. My last example, y equals the negative cube root of 27x minus 81 plus 3. I'm going to factor out a 27. That gives me x minus 3 on the inside, plus 3 on the outside. I'm going to simplify the 27. Y equals a negative cube root of 27 is 3. X minus 3 on the inside, plus 3 on the outside. So this is going to give me y equals the cube root of x as the family of functions. I'm reflecting over the x. I have a stretch of 3, a shift to the right 3 units, and a shift up of 3 units.